Log on, tune in, find out. Another good idea from Cambridge.
The first speaker is Tamas Hausel, who will talk on arithmetic and physics of Higgs moduli spaces.
Thank you very much. Is this working? Yeah? Okay, that's all. Yeah. So thank you very much for the invitation. Today I'm going to talk about a nice occurrence of a relationship between arithmetic and physics via the geometry of Higgs moduli spaces. In fact, until recently I could have given a talk with the same title, but where both the arithmetic aspects and the physics aspects would have been different. So for the arithmetic, you might be aware of the work of Guobao Chao, where he used basically the topology of the Hitchin fibration, whose total space is this moduli space of Higgs bundles, to prove the fundamental lemma in the Lagrange program. And on the physics side, the connection was the work of Kapustin and Witten, reducing S-duality from 4 dimensions to 2 dimensions. But today I'm going to talk about two different aspects, both in the arithmetic and the physics, and again the connection will be provided by the geometry of the moduli space of Higgs bundles. So the arithmetic will be our work on the mixed Hodge polynomials of character varieties with Fernando Rodriguez Villegas, and the physics will be a very recent work of Chuang, Diaconescu, and Penn. And in fact, Diaconescu has given several talks on already in this program. So I think it's actually good to have a mathematician's point of view of my sort of understanding of what they are saying and how the cohomology of the moduli space of Higgs bundles appears in M theory in terms of in terms of BPS state counting. So let me introduce you first the spaces, and I'll tell you about this arithmetic approach to attack the question of calculating the cohomology of the moduli space of Higgs bundles. And then in the second part of the talk I will give this introduction or some sort of understanding of what the physicists are saying about the cohomology of the Higgs moduli spaces. So let me start with introducing the varieties which we will study. So we will fix a genus G smooth projective curve and for today's talk we will fix the group GLN. Well, fixing meaning that we just choose GLN. N might vary, and it will vary. In some formulas we will have N running, but it's really just GLN case which we will study today. And so this moduli space of Higgs bundles, which many of you are aware of, is a moduli space which you can define as a moduli space of semi-stable rank n and degree d Higgs bundles. And those of you who haven't heard of this yet, a Higgs bundle is of course a pair of rank n vector bundle E. The degree is fixed to be this d, and phi is the Higgs field, which is just an auxiliary scalar field, sort of scalar field with which is really just a canonical bundle valued endomorphism of the vector bundle E. And there is a natural notion of semi-stability for such objects, and then one can construct a moduli space parametrizing them. So that's one of the varieties which will appear, and there is another algebraic variety in many ways really different, and this is the character variety which we attach again to the same data, to GLN and this D. So the variety is really just the character variety of representations of the fundamental group of the Riemann surface C. So we have this genus G curve, it has this underlying Riemann surface. You take the fundamental group of that, and then you study the representations of that fundamental group into GLN, and we will take the variety of characters of these representations. So that's what we have here in a very simple way of presenting the fundamental group as the canonical, the standard way, choosing 2G matrices, one for each generators of the fundamental group. The only equation we will impose is that the product of commutators Well, if it was just an honest representation of the fundamental group, then we would have the identity here, but in order to match this twist in the degree of the Higgs bundle, we will have this dth power of and primitive nth root of unity scalar number on the diagonal of this matrix. So really this is twisted representations of the fundamental group. Then because we are interested in characters, we will divide by the adjoint action of GLN on these representations. So these varieties are really different on the face of it, because this is an affine variety just by construction, and this one is a quasi-projective variety with large projective subvarieties. So algebraic geometry of the two varieties are really different. However, they will share their topology, and that's so for now. Let's just say first that the case we will be concentrating on when D and N are co-prime. That's why we really chose this twisting in here. Then the varieties will be non-singular. That's going to be important because we will be interested in their cohomology. And the other aspect which is important for the topology is that they are non-compact. As I said, this was an affine variety and this is a quasi-projective variety. But what connects them is a diffeomorphism between the two varieties. There is a canonical diffeomorphism which you can formulate in a conceptual way as the non-abelian Hodge theorem, that there is a canonical diffeomorphism between the moduli space of Higgs bundles and the representations of the fundamental group. So one way to think about this is really just non-abelian Hodge theorem, and the other way to think about this is to note, as in the original introduction of this space by Nigel Hitchin, that this moduli space of Higgs bundles comes equipped with a natural hyperkiller metric, and in one complex structure the algebraic reincarnation of the complex manifold is this moduli space, and in another complex structure, well, one algebraic reincarnation is this character variety. So what we really see somehow the algebraic geometry of this twistor space of this hyperkiller metric, if you like. But what's important for us is going to be that they are diffeomorphic, they will share the same cohomology groups. So this non-abelian Hodge theorem is the work of many people, listed here. Just in order to give you some simple example, I will always run this example of genus equals 1, because it's known completely, but it's also non-trivial. So when genus equals 1, one can think about only one commutator here equal this twisted central element, and then you can really think of this is in terms of some representation of some version of the Heisenberg group, and by just some analog of the Stone von Neumann theorem, you can see that up to scalar multiplication there is a unique such solution of that equation. So what it says about the variety, which you can explicitly prove, is that no matter what n is for genus 1, this twisted character variety is always just these scalars, this C star to the 2. So it's always the same two-dimensional torus. On the Higgs side, what you can show is that you can parameterize these genus 1 twisted Higgs bundles by points of the cotangent bundle of the elliptic curve itself. The Jacobian of the genus 1 curve is just the cotangent bundle of the elliptic curve itself. It's a different algebraic structure, but the topology is shared. They have the same cohomology. So the main problem, which I have been studying basically all my adult life, is try to determine the cohomology, the Betti numbers to start with, of these varieties. So originally it was the moduli space of Higgs bundles. The reason you might be interested in this, because there is a Kähler version of the same construction, the moduli space of stable bundles, and this has a very nice and long history, and in many ways that is very well understood by now, and then it would be the first natural hyperkiller version of that story. Can we calculate the Betti numbers of the moduli space of Higgs bundles? And it turns out that this is still an open question, even 24 or so years after the introduction of these moduli space of Higgs bundles. We still don't know what the Betti numbers is for general n. Only very recently we had Oscar Garcia Prada and Heinlott and Schmidt did the n is 4 case after 24 years, and so that's very good, but still n is 4 is not all n, and we still don't know the Betti numbers. So today what I will show you that you can use an arithmetic technique to get information, some sort of information. You will see, unfortunately, it's not a determination of the Betty numbers, but we will at least come up with a conjecture on the Betty numbers. Well, on the first hand, it's not on the moduli space of Higgs bundles, but the character variety. But because of the non-abelian-Hodge theorem, the information then can be translated back to the moduli space of Higgs bundles, and we will see that in fact that the extra structure we find here will have a corresponding extra structure here, and somehow that extra structure is the one which will lead us to physics in a natural way. So the technique, I will show you this arithmetic technique, will use the fact that this character variety is a very simple affine variety. It's given just by a single equation, a single matrix equation, and we will see that the arithmetic of this variety is fairly simple to handle. And by arithmetic, what I mean is to study the variety over a finite field. What we will do, we will be able to count points of this variety over a finite field. The reason we will be able to do that, because it's a single equation, there will be a nice formula which will evaluate the number of solutions of this equation now over a finite field, which only means to look at these matrices not in GL and C, but in GL and FQ. And for that, we will have a nice character formula. We will be able to evaluate the number of points. But okay, so what if we know the number of points of the variety over a finite field? What sort of cohomological information it will give us? So that's the theory of mixed Hodge polynomials, or the mixed Hodge structure of the Lie, which is needed to formulate the connection between arithmetic of an open variety, this is a non-compact affine variety in particular, and the arithmetic of the variety. So this is going to be crucial for what follows, is that in fact, the Lie was motivated by arithmetic considerations, that there is an extra structure on the cohomology of any smooth, any complex algebraic variety, not necessarily smooth or projective. And that's an extra filtration, which is canonical, functorial, and it has all kind of nice properties. And that's the so-called weight filtration. It's an extra filtration. You can somehow assign weights to cohomology classes, and you might have different weights in a given cohomology. For a smooth projective variety, the case you might have been more familiar with, it's actually trivial, the weight filtration, so it's nothing interesting there. But for an affine variety like this one, it will be a really non-trivial extra filtration on the cohomology. So instead of then being interested in the Betty numbers, you might be a little bit more ambitious and be interested in the dimensions of the graded pieces of the weight filtration on the cohomology. So it's one more variable you have to worry about, not just the Betty numbers, which would be the dimension of the cohomology, but also the dimensions of the graded pieces of the weight filtration. So of course this has more information, this two-variable polynomial, because if I forget about the weight filtration, that is, I set Q to be 1, then I get back the Poincaré polynomial. So it would be very nice to be able to determine the mixed Hodge polynomial, say, of the character variety. But what the arithmetic tells us, unfortunately, is not a technique to determine the mixed Hodge polynomial. It is another specialization of the mixed Hodge polynomial which the arithmetic helps us to determine. And this specialization, which is basically just an Euler characteristic kind of specialization at t equals -1, I also do a Poincaré duality sort of approach here, because the E polynomial which we are defining here really is defined on the compactly supported cohomology of the variety. And so this definition here makes sense for a smooth variety. It's the E polynomial can be calculated from the mixed Hodge polynomial on ordinary cohomology like this. So the E polynomial, or virtual Hodge polynomial you might have heard of, or weight polynomial, or Serre polynomial, all kinds of names, have this very amazing property, many very nice properties, but basically is that it's computable. Unlike the cohomology, for example, it's additive when you decompose your variety into disjoint union of locally closed subvarieties. You just calculate the E polynomial of the pieces, you add them together, and you do get the E polynomial of the whole space. Of course, this is not true about the cohomology, but the E polynomials are really nice. They are additive, they are multiplicative. And in fact, the reason they behave so nicely is that they are somehow modeled on the arithmetic of the variety. And of course, counting points is naturally an additive operation and multiplicative and whatever the E polynomial satisfies. So there is a deep connection between E polynomials of complex varieties and the arithmetic of the variety over a finite field. And so one of the incarnation of such a connection is our technical result, which is going to be linking for us the arithmetic of the variety, that is the number of points of the variety over a finite field, with this E polynomial, which will give us at least one look at what the mixed Hodge polynomial might look like. We will get from this arithmetic technique this specialization, the E polynomial. So the theorem which we will be using concerns a very small class of varieties. So this is a very special result which we are using, but fortunately for our character varieties they will have this property. And the property which we have to assume is what we call polynomial count varieties. What we have to assume is that the variety, when you count its points over a finite field, that as a function of the order of the finite field, that is Q, is a polynomial in Q. So how do you say that? I mean, if you haven't heard of schemes, the best way to just think about is somehow the variety being defined over the integers, meaning it's given by equations where the coefficients are integers. Then you can consider the same equations over, say, modulo a prime over Fp, the prime fields, or over any finite field. And then now you have equations over finite fields, you can count points. And then the polynomial count assumption is that this count as a function of Q is a polynomial in Q. It happens very rarely, of course. Already for an elliptic curve is famously a very hard problem to get the formula for the number of points. It's clearly not going to be a polynomial. But for some varieties, like toric varieties from the smooth projective world, or character varieties, have this nice property that they have a very nice count over a finite field. And in that case, we have a very straightforward connection between the topology, the cohomology of the variety over the complex numbers, and this count polynomial. It is really just the Weyl conjectures in disguise for this class of varieties, but the connection is very straightforward. Unlike in the Weyl conjectures, you don't have to mess with zeta functions. You just take this count polynomial, and this is on the nose the same as the E polynomial. Of course, this also hints at this connection I said about the additivity, because the count is clearly additive, and then so it's very nice when then the E polynomial is rather be additive too. Okay, so this is going to be the technique which we will be able to use for the character variety, and the reason for that you can actually evaluate the number of solutions of that equation. If you remember this matrix equation of the commutators of those 2G matrices multiplying to the twisted identity, you can actually count the number of solutions of that equation. So what you can do is that you can evaluate the number of points of this variety over a finite field, and the technique which helps you is basically a result, a character formula result, which goes back to Frobenius. If you want to count, now what we are doing, we are counting number of solutions of this particular equation now in some finite group, which is just GLNFQ, and then it turns out that the form of the equation, it's coming from the relation of the fundamental group of a Riemann surface is exactly one, so that we have this very nice character formula for all irreducible characters of this finite group, which is just GLNFQ. We have to evaluate this quantity, which only remembers the value of the irreducible characters on this central element. What we need is this central element zeta n to the d to be inside my finite field, and divided by the dimension of the character, and then some constant in front like that. Anyway, if you've seen the Ferlinde formula, it actually has a similar flavor. It comes from some topological quantum field theory approach. At any rate, you can then evaluate this. You can go there and calculate this, and what you will get is a polynomial. You can prove that the result is a polynomial. It's not a priori, it's just after calculation. You will find that as a function of Q, this is a polynomial, and now you can deduce that this is just the E polynomial of the variety over the complex numbers. So there are several surprising properties of this character formula when you work with it and evaluate these expressions. One is that the dependence on D is very mild. Basically, if I have an nth root of unity inside my finite field, then there is always a Galois conjugation I can do of the finite field, which will send one nth root of unity to the other. And of course, the character theory is somehow invariant under this Galois conjugation. And so these formulas don't depend on exactly which d you are taking. So this is the first thing which we noticed just by the very fact that we can evaluate the number of points with this character formula. The result will be independent of which d we picked. So in just what we need, of course, is the d and nr co-prime, exactly as d prime and nr co-prime. The e polynomials of the character varieties are the same. And in fact, you can push this even more, because it's not just the varieties are Galois conjugate over the finite field, there's somehow there is some Galois conjugate over the complex numbers. There is a field automorphisms of the complex numbers sending this one nth root of primitive nth root of unity to the other, and then somehow the cohomology can be calculated algebraically, and so this will give you an isomorphism on the mixed-Hodge structures of these varieties. So the mixed-Hodge polynomials will then be independent of this d, and this is the first really surprising aspect. For example, we see that the Poincaré polynomials will be independent of d. They will only depend on n. And if you have worked with the moduli space of stable bundles, you know this is not the case there. So this is somehow a surprising aspect of the cohomology of the moduli space of Higgs bundles, even though we don't see the geometrical connection then between the spaces when d and d prime are co-prime to n, still somehow their Poincaré polynomials are the same. I mean, this shows that this for the character variety and therefore for the Higgs moduli space. So that's a very first surprising aspect. But then you see that now this thing only depends on n. So probably in this formula I should have changed d with n somehow. And then what we did, so what we did, as I said, that we evaluated these formulas explicitly. We had a combinatorial formula, basically a formula like this for the e polynomial of the character varieties. When you evaluate this with the irreducible characters of finite fields, you will find yourself writing down partitions. Partitions are labeling irreducible representations of the Weyl group Sn, the symmetric group. And then somehow from those irreducible representations, combinatorially, you can build up the representations of GLNFQ. And this formula here, now you see, is somehow a refined version of our original calculation with Fernando. So in the left-hand side, we see the sum of over all partitions of n for every n. So it's the size of the partition here. So it's a huge sum over all partitions of n. Again, you should think of philosophically, it labels the irreducible representations of Sn because they are inputting into the representation theory of GLNFQ. And the connection between the representation theory of GLNFQ and Sn is via this formalism. On the right-hand side, we see, well, it's not just the e polynomial, as this formula says, but this is conjecturally the mixed-Hodge polynomial of the character variety appears here. Again, this should probably be n instead of d. To remember, this is the GLN character variety. For every d which is co-prime to n, we know it will be independent. And then you combine them together in this complicated way. So for n and k, we sum up all these mixed-Hodge polynomials of all the character varieties for every n. And then they start to mix together, and then when they mix together, the conjecture says that you should get what's on the left-hand side. So how did we get to this conjecture? Of course, it's a long story, but what we did again, we calculated the e polynomial, which is some specialization of this one, and then what we tried to do, we were trying to deform that calculation, and that conjecturally became this formula. But of course, we had the guiding result was that for n is 2, with Michael Thaddeus, we managed to calculate the cohomology ring of these Higgs moduli spaces, and therefore the character varieties explicitly. And using that explicit formula, we could actually get for n is 2 the mixed-Hodge polynomial of the character varieties. So that was the guiding principle, but eventually this whole effort came together to this one-line neat conjecture about the mixed-Hodge polynomials of all character varieties. And this is a conjecture because mixed-Hodge polynomials we don't know how to attack from with arithmetic techniques. Let me show you, for example, the genus equals 1 case, because in that case, of course, the input, all these character varieties are just tori. In that case, the left-hand side, the genus 1 case is just going to be this. Again, here, unfortunately, Q is taking the place of lambda, which is really unfortunate, but Anyway, in the right-hand side, we see that it's always a torus. So it's here we see the mixed-Hodge polynomial of the torus, and then these t's got add up when n went from 1 to infinity here. At any rate, what you have, just because you know what the character variety is, you have a combinatorial formula, which we cannot prove, or we couldn't prove. So this formula, although can be checked with computer up to any large n, or until your computer dies, still is always correct. It is a refinement of Euler's famous formula about partitions, and then the other specialization too can be calculated. Many specializations of this formula can be proved, but combinatorially, even today, we cannot have a proof. But at the end, I will report that using these physicist ideas, at least I now see a geometrical proof in a completely different universe. Okay, so this is the conjecture, the main conjecture, which will be crucial what comes later. So let me show you another curious aspect of the calculations, if you like, and the further results. The so-called, that there will be a surprisingly a sort of Harlefschatz theorem, conjecturally at least, satisfied in the cohomology of the character variety. And so this was already apparent when we did the calculation. So we evaluated, of course, the E polynomials using these character formulas. You do those calculations, and at the end you have a polynomial in Q, as I told you. But these are not any polynomials, they are palindromic. They read the same way backwards than forward. Coefficients surprisingly match up. In every case, for every n, you get this surprising property that this affine variety has an E polynomial which is palindromic. It's not expected. You will have negative coefficients, so this is unlike what you might have seen for smooth projective varieties. So it satisfies this functional equation. That's, if it was the Poincaré polynomial, it would just be Poincaré duality, but this is a weirder sort of what we call a curious Poincaré duality. And the nice thing is that it actually has a reason from the representation theory of GLN, because the characters come in pairs, and in fact that duality, the Alvis-Curtis duality, is really responsible for this symmetry, for this functional equation. The characters come in pairs, and their values on irreducible characters are related exactly, so that this palindromicity happens. So somehow deeply, because of some deep fact about the representations of GLNFQ, we have this palindromicity. But this is not just a palindromicity, this was also a fuel in our guessing game, trying to get the extension to mixed-Hodge polynomials that we hoped, and in fact for NS2 we could calculate that the symmetry persists on the level of the mixed-Hodge polynomial. And then it's not just that it persists, it comes to say the two pieces of the graded filtration of the weight weight filtration on the character variety has the same dimension, and those bits in fact are connected by a Harlefschatz sort of map. So here is the statement, what we noticed, and what we could prove using our earlier calculation with Michael Thaddeus, that for n is 2 we could prove it, and for every n what we conjecture is that there is a curious Harlefschatz theorem done by a class in the degree 2 class, which is not, as you would guess from a Harlefschatz theorem, it's not type 1,1, it's type 2,2. It's a weight 4 class. And somehow, still, there is a natural map from this graded piece of the weight filtration to this one. Conjecturally, they have the same dimension, and then the conjecture is that this map is an isomorphism. This would be a curious Harlefschatz conjecture or theorem if we could prove it. But it's really, really surprising that an affine variety would satisfy such a symmetry in its cohomology. And the other one, of course, is that the mixed-Hodge polynomial, in fact, satisfies this functional equation, which is just to say that these dimensions are the same. If you had remembered, I had Z and W in that formula, and then everything was symmetric in Z and W. And that extra symmetry somehow explains why we have this extra symmetry in the mixed-Hodge numbers of the character varieties. Okay, so we still don't know why this is true, but at least now there is a very nice other conjecture, which if it was proved would explain the reason why we have a mixed-Hodge, why we have a curious Harlefschatz conjecture. And the reason is that there is a reincarnation of a different sort of Harlefschatz theorem, which is true on the cohomology of a non-compact variety. And that's the so-called relative Harlefschatz theorem in this case, but that will use a different filtration on the cohomology. We had now the weight filtration of the cohomology which made this symmetry happen, but there is a different filtration on the cohomology of now in a completely different setup for the total space of any proper map between complex algebraic varieties. One can introduce, as did De Cataldo and Migliorini, one can introduce a filtration in the cohomology of the total space of any proper map. Originally, they were studying the decomposition theorem, via which you can decompose the direct push forward of the constant sheaf on the total space of the fibration to the base, and then there is the decomposition theorem which decomposes it into in non-canonical way into sum of perverse sheaves, and although it's non-canonical, the corresponding filtration you get when you pass to hypercohomology or cohomology of this complex, which will just be the cohomology of the total space, will inherit a canonical filtration. So that's conceptually the reason why there is a filtration. It comes from the decomposition theorem. There is a more down-to-earth definition, again due to them, of this in the case when the total space is smooth and the base is affine, which will be the case we will have here. And I show you this because this one will at least give you a better feeling of what this perverse filtration measures. So what you do is that now you have this affine base space, and you take a flag of subvarieties, one for each dimension. You will have to assure that some of these subvarieties are generic in a well-defined technical sense. The point is that they are supposed to intersect transversally all the discriminantal loci of the fibration. So the fibration could be very complicated, fibers getting more and more singular. You will have various strata in the base, somehow remembering the degenerations, and then all these test subvarieties in the base should be transversal to each of them. Anyway, there is some genericity condition which can be and should be satisfied, and in that case the perverse filtration is nothing but the filtration on the cohomology which measures how cohomology classes vanish over which test subvariety. So what you do, you take a cohomology class in, say, degree k, and then you restrict it over the ith test variety, over the fibration over that ith subvariety, I-dimensional subvariety, and then you look at those cohomology classes which go to 0, and they will form one bit of the perverse filtration. So you see, this really somehow measures the way how the fibers become singular, how cohomology classes get absorbed in the singularities of the fibration. It really remembers the topology of the fibration. So one case is, of course, always very interesting when we have a point that is y0 is a generic point. What we are doing, we are restricting to the generic fiber of the map, and we are looking for the kernel of which cohomology classes go 0 to the generic fiber of the map. That will be one part of the perverse filtration. Okay, so this really just another filtration, but what it satisfies, and this really is the reason this is so nice, and this really goes back to the original decomposition theorem, which was motivated by understanding the Harel-Lefschetz theorem and all the Lefschetz package on the cohomology of varieties in a family, and even a degenerating family. And so the relative Harel-Lefschetz is a theorem here which holds for the graded pieces of the perverse filtration on the total space of a proper fibration. In this case, you will take a relative ample class, which is now a normal type 1 class on the total space, and that one will induce an isomorphism between the graded pieces of the perverse filtration on the total space of this proper map. And this was what my colleagues De Cataldo and Migliorini were aware of, and then when they heard the symmetry, this curious Harel-Lefschetz conjecture we were suggesting with Fernando Rodriguez Villegas, they said, oh, we have seen such a filtration on the cohomology of the non-compact variety before, namely this one, so maybe there is a connection between the two which might explain curious Harel-Lefschetz theorem. And then, of course, in our story, there is a famous proper map. And the famous proper map is the Hitchin map. On the total space now, going back to the cohomology of the moduli, going back to the moduli space of Higgs bundles, on the total space of the moduli space of Higgs bundles, we can take the characteristic polynomial of the Higgs field, and this will end in an affine space of half of the dimension of the moduli space of Higgs bundles. And this will give us the famous integrable system, the Hitchin integrable system, which is, moreover, is going to be proper. So we have a proper integrable system, The integrability yields, for example, that the fibers will be abelian varieties, will be tori. And then, of course, now you could have guessed, if you were them, and as they did, you could have guessed that maybe the reason that Curious-Harleshet's holds is that you can match the perverse filtration on the moduli space of Higgs bundles induced by the Hitchin map with the weight filtration on the character variety via under the isomorphism when you identify the cohomologies by non-abelian Hodge theorem. And then this we conjectured, or they conjectured first, just basically trying to understand why Curious-Harleshet's theorem might hold on the character variety. So one immediate aspect of this, for example, was the first thing we then started to do, we had to understand the cohomology of the Hitchin fibration for n is 2 or for a higher n. The one thing you can first do is to reduce to the generic fiber of the Hitchin map. And we were lucky because Michael Feathers had it in his diploma thesis, a calculation of what the cohomology goes, what happens to the cohomology of the moduli space of Higgs bundles when you restrict to a generic fiber. And then there you could see that those classes go to 0 exactly, which are predicted by this conjecture. So this was the starting point when things seemed to be working, just because the topology of the Hitchin fibration miraculously seemed to mirror the arithmetic or the weight filtration on the cohomology of the character variety. And then what then later turned out that the sort of calculations we had to do in order to evaluate the perverse filtration, that's a hard thing to evaluate, the perverse filtration. On the other hand, the weight filtration is nice. It has very nice properties, but because of this conjecture, now the perverse filtration, at least for the Higgs moduli space, must also have very nice properties. For example, it's multiplicative, but these things are absolutely non-obvious and unclear why this might hold for the Higgs moduli space. But then you start to do calculations, you will go to more and more singular fibers of the Hitchin map, and for n is 2, eventually putting together all the known cohomological results in the cohomology of the moduli space of rank 2 Higgs bundles, all together with a really brute force calculation, we managed to push this to a theorem. So now this is a theorem that the perverse filtration and the weight filtration agrees when n is 2. It's not a conceptual theorem, it's a calculational one. We prove that the perverse filtration satisfies as much property as the weight filtration does, and eventually things are forced to be working. But what's amazing is that the actual calculation is really just mirroring Engo's strategy of proving the fundamental lemma. I told you he was studying the fibers of the Hitchin map, the singular fibers, but he was also studying exactly the same decomposition theorem. Basically what he was studying was the perverse filtration, not on the total space of the moduli space of Higgs bundles, but on the singular fibers. But his sort of calculations are really very similar to ours, except that, of course, we only work for GL2 in this case, and of course, Engo works with any reductive group. So what we do is a very special case, and it compares to a very special case of Engo's proof of the fundamental lemma. Okay, so that's the case story for n is 2, so it's now done. But what about higher n? This is such a nice conjecture, and then the Curious-Harleshet theorem is thought to be holding for every n. You can show that the E polynomial is palindromic. So there are all kinds of symmetry assumptions which make you believe this must be true for higher n as well. But my colleagues are more cautious than I am, so we were wondering, do we formulate a theorem or a conjecture that P equals W for every n, or we just leave this open, this case? I mean, I would have said from the very beginning such a nice thing ought to be true. But I will show you now that there is a surprising source of an evidence for this, and this comes from physics. This M theory of some 11-dimensional variety, somehow the BP states in that theory, whatever they are, somehow relate to the perverse filtration on the cohomology of the Higgs moduli space. And this is really surprising. How could physics say anything about the perverse filtration when it uses the decomposition theorem and perverse sheaves, which are highly non-trivial mathematical constructs? And what we will see is that it's not really the perverse filtration they can talk about, but what they can see in their physical picture is a symmetry which comes from the relative hard-Lefschetz. So relative hard-Lefschetz, whenever you have relative hard-Lefschetz or hard-Lefschetz, you can always define an action of the Lie algebra SL2 on the vector space. And that's the symmetry which somehow comes from physics. They see an action of SL2 on the cohomology of the Higgs moduli space, which should be which should be the one which is given by the perverse filtration. So that's now the next story, and this will be a lot of physics now, and so it will be very vague, and not just because it's physics, also things, the mathematical things will not necessarily be defined, and there will be huge formulas, and I wouldn't watch for them, but they should be giving you a rough idea how physicists can use various duality conjectures in physics to give a conjecture eventually on the dimension of graded pieces of the perverse filtration of the moduli space of Higgs bundles. And so this is a recent work of Chuang, Diaconescu, and Penn, which Diaconescu was lecturing about this in Oxford in March, for example. And unfortunately, there is no publication on this newest work yet. So what I will tell you again is some ideas that they are putting forward. So this is going to be a really different physics. Instead of doing Riemann surfaces, like Orbatati Abbott did Young-Mills theory on 2 dimensions, or even what Kapustin-Wittenting did S-duality in 4 dimensions, instead this is going to be string theory. We will be starting to study a Calabi-Yau threefold and some partition functions attached to this in string theory. And so this is going to be a somewhat special example. It's not your usual Calabi-Yau threefold, what a physicist would really like to study. That is not a compact Calabi-Yau threefold, smooth Calabi-Yau threefold. It will be an open Calabi-Yau threefold. And then the advantage will be that you will be able to do more calculations, but the disadvantage will be that, of course, things will not be compact. So a lot of the compactness will cause problem with non-compactness will arise. So the Calabi-Yau threefold, in our case, is going to be a rank 2 bundle, the total space of a rank 2 bundle on the Riemann surface, or the smooth projective curve C. Namely, you take the trivial bundle plus the canonical bundle. So this is set up so that it is going to be a Calabi-Yau threefold, and then you can do string theory on this, somehow what we say locally around the curve, or you can do it equivariantly. There are techniques to be able to talk about the partition functions of string theory in a local model like this. So it's called the local curve in this story. But we will be interested in what string theory looks like around the zero section of this vibration. Okay, so now comes one of the partition functions which Diaconescu calls Donaldson-Thomas partition function on the invariance. I renamed it Pandari-Panda-Thomas because in the definition they use the moduli space of stable pairs due to Pandari-Panda-Thomas. So this, as they say, the physicists, this should be a refined way to define the partition function of the type 2A closed string theory on this local Calabi-Yau threefold. So let me just say a few words about this mathematically. It's not defined, that's to start with. It's a quantum version of Pandari-Panda-Thomas invariance, or refined version or motivic version. As it is, it's not defined. What's defined, the unquantum version, the one specialization of this is defined. That's what Pandari-Panda-Thomas studies. But for us, we will need the refined version. So what's in here is a generating function of invariance of the moduli space of stable pairs on the Calabi-Yau. And the stable pair roughly is a sheaf with a one-dimensional support and then some section of it. Somehow it's a little bit like Higgs bundles. It's a pair of objects. You have some stability condition. You define a moduli space. And then what's not defined is what this virtual E polynomial, or what's the virtual motif of this variety should be. Somehow it's not defined. What's defined is the Euler characteristic. So when you set y equals 1 or minus 1 in this formula, that's defined. That's the usual story of Pandari-Panda-Thomas or Donaldson-Thomas invariance. Non-trivial, because these varieties are very singular. They only have virtual Euler numbers. But well, what we will need is this refined version. We will want to talk about virtual E polynomials of these singular varieties. So this is a not defined thing, but still physicists can talk about it. So that's an invariant attached to a string theory on that Calabi-Yau threefold. There is a corresponding M theory. You can multiply C2 times this Calabi-Yau threefold with an S1. You will have an 11-dimensional variety. And on this, the invariants are getting out of reach of geometry for the time being. But the physicists can talk about some invariants they can attach to this string, to this M theory on this 11-dimensional space. And these are these BPS invariants. And then the BPS invariants are one thing. So originally Gopakumar and Wafa considered the usual BPS invariants, and here we will be considering the refined BPS invariants. It is a big generating function, and then these mysterious BPS invariants are there. They are integers as they are constructed. Then you form this big generating function out of them. And then in the next slide, at least, I'll show you what it is in our case. For a local curve, we will give, and that's, I think, the major insight of Diaconescu and then others, that you can give a geometrical meaning for the case of a local curve of these BPS states, these BPS invariants, using the perverse filtration on the cohomology of the Higgs moduli space. You will see on the next slide. So, but for now, what again comes the first duality what the physicists are using in this argument, and that's what you can call a refined BPS conjecture or a refined Gopakumar-Wafa conjecture, is that there is this connection between these two partition functions. This partition function of the string theory on the 6-dimensional Calabi-Yau is the same as this invariance coming from M theory. Again, so what we will do here, I don't understand, this is a duality between type 2A string theory and M theory somehow, so something difficult in physics, but until recently this was really hard to understand the right-hand side. In fact, mathematicians were understanding these BPS invariants via this conjecture. They could calculate this in the unrefined case, and that's how they could think about these integers. But now, thanks to the work of Chuang and Diaconescu and Penn, there is a geometrical way to try to think about these BPS invariants. So that comes in the next slide. So what are, in the case of a local curve, what a mathematician might think of these BPS invariants? Okay, so they are labeled by different numbers than what I had in the previous slide. They are labeled by these JL and JR, and then the beta, of course, is always just the homology class of the support of the sheaves we are considering. And then these invariants, there was always, in fact, a geometrical sort of intuition behind them, but the problem with that was that for a general Calabi-Yau threefold, or the ones they considered, the moduli space, which we will be talking about, are very singular, very hard to understand. So heuristically, the geometrical way that the physicists thought about these BPS states, that it arose from decomposing the cohomology of some space, which is the heartbeat in the mathematical story, is the space of D-branes on your Calabi-Yau threefold. And then what do you decompose it against? You decompose it against the symmetry group acting, or Lie algebra in this case, acting on the cohomology. And this comes from physics, heuristics, why you must need an action. And this is actually the spin 4, I believe. Why do you have this symmetry group in the story? It comes from the physics. But at any rate, what we have is, and they always said this very vague argument that there must be some moduli space of D-branes living on the Calabi-Yau threefold, whose cohomology will come naturally equipped with these symmetry groups. And when you decompose it according to irreducible representations of these two SL2s, you will get, for each irreducible representation of the left SL2 and each irreducible representation of the right SL2, you will have a multiplicity of that representation of the product inside the cohomology, and that should be the BPS state, in fact the refined BPS state, BPS invariant. Okay, so now let me tell you how this relates to Higgs bundles, or that's what the Diaconescu are saying, that you can think about, again, this is not really well defined, these D-branes, but again, these are sort of sheaves on the Calabi-Yau threefold with a one-dimensional support. And basically, they can argue that in this case, you can have a stability condition maybe on them, or some other way you can identify these sort of sheaves on the Calabi-Yau threefold, the local curve, with Higgs bundles on the base. This is a sort of Bovil-Narasimhan-Ramanan sort of identification of sheaves, not on the cotangent bundle of the curve now, but on this rank 2 bundle and the moduli space of Higgs bundle. It's really actually that sort of connection they do here. But anyway, so now we have this moduli space of Higgs bundles appearing as a good choice maybe of this moduli space of D branes on this local curve. So there are some numerics here which I'm copying from the talk of his maybe. How for beta, you remember, was the homology class of the support of the sheaf. So it will be now n times of the zero section, and then here is how you get D from rank n, and E was the here the I guess the Euler characteristic of the sheaf. Anyway, so there is a way to connect these spaces. At least this is very heuristical because this is not really well defined. But now what we have, and in fact this is already was present in the original thinking about these SL2 times SL2 action, what the physicists were saying, look at these D branes, forget about that they are sheaves, just look at the support is going to be a curve, take the moduli space of curves inside your Calabi-Yau threefold, you will have a map. In fact, it will be like a Hitchin map, you will have some proper map. Everything here is projective if your variety Calabi-Yau threefold was projective, and first do relative Hard-Lefschetz with respect to that map, or they were not saying that, but you can do relative Hard-Lefschetz theorem with the perverse filtration on the total space. That will give you one of the SL2 actions, and then just do your usual Hard-Lefschetz because it's a projective variety on the right hand side. So you have these two actions of SL2, and they should arise from Hodge theory on this vibration. That was the original. I mean, they were thinking about this back then, but the problem in the case of a projective Calabi-Yau that these varieties are very complicated and not absolutely not clear how to define. But in our case, we can identify a good candidate for the space of D branes is the moduli space of Higgs bundles. And then if you think about this idea of taking the support of the sheaf, it's like just taking the spectral curve of the Higgs bundle. It's really just nothing but the Hitchin map. Is this map of forgetting the sheaf structure, just remembering the support of the sheaf. So that's really just the Hitchin map. And then what we know, of course, is now that we have the perverse filtration induced on the cohomology of the Higgs moduli space, which comes with the relative Hard-Lefschetz theorem. And then if you have a relative Hard-Lefschetz theorem on the gradient of the perverse filtration, that will lead you to a canonical definition of an SL2 action on the graded pieces of the perverse filtration on the Higgs moduli space. So that's how we will see the left SL2 action in this story. You remember what we want? We will want to decompose the cohomology of the Higgs moduli space according to these two actions. But because we are in the non-compact case, in the local case, somehow it's unclear what this SL2 right should be. But now comes Diaconescu some hand waving saying maybe in this case what he can define is not a full SL2, but he can define some weighting using the primitive decomposition. At any rate, you will have somehow cooked up from the perverse filtration, you can cook up not just a GL2 action, SL2 action, but you can also cook up a GL1 action. Well, at any rate, what we can do, and that's what I do, is just to take what they define, these refined BPS invariants, to the dimension of some pieces of the primitive decomposition of the perverse filtration on the moduli space of Higgs bundle. So now this is a well-defined definition. Now this is mathematics from this on the right-hand side of this refined Gopo-Kamarbova conjecture. In fact, are going to have as much information as the graded pieces, all the dimensions of the graded pieces of the perverse filtration somehow will be repackaged with these decompositions into these actions. Okay, so that explains the right-hand side. Now mathematically, at least, I can take. Exactly, that was the motivation behind this. They understood it back then 10 years ago, but the projective case, it was very hard. The varieties were not normal, and so yeah, that's the pattern here which they follow, Diaconescu follow. So how do you now, how do you calculate these refined Pandari-Pandit Tamas invariants on the other side of this conjecture? I mean, one thing, they are not defined, but physicists are not, they don't find that an obstacle to formulate conjectures about them. Namely, and there is going to be this amazing conjecture. We already had one duality, right? This M theory type 2A string theory conjecture, but here is going to be an even more baffling one from the mathematics point of view. They say that this string theory partition function should be possible to be described by some gauge theory partition function, and now this is going to be a much simpler sort of physics. It's just going to be gauge theory in a four-dimensional manifold. So there will be no string theory on the other side. It's really, really surprising that you can do this. And then the duality here runs by the name of geometric engineering, which is somewhat counterintuitive in our direction, because we start with the Calabi-Yau. We have the refined Pandari-Thomas invariance of the local curve, and we are looking for the gauge theory. Normally, it's done the other way. That's why geometric engineering really means, to a gauge theory, can you find the string theory whose some partition function of that will recover the partition function of the gauge theory, geometrically engineer the gauge theory to get a Calabi-Yau. But we are somehow doing it the other direction. So let me show you what they say in this story the gauge theory should be. So the nice thing will be, of course, that this way we will get an explicit conjecture about these not yet defined refined Pandari-Thomas invariants. So what they say is that this should be a U1 gauge theory somehow on 4 dimensions, and there is no topology in the base. It's just R4 or C2 if you like. So it's really, really surprising. Where is going to be the, you remember we are talking about in the left-hand side the local curve. We have a genus G Riemann surface. It's this rank 2 bundle over this. And then they say that the partition function of this string theory should be the same as some U1 gauge theory on this R4. But of course, in order to see, for example, the G, somewhere you have to put in the gauge theory the G. And this will come in the, what they say, the matter content or the field content, I think that they were in the theory. So let me show you now. Just, I take it as a definition as a mathematician, and this is a safe thing to do. We just take that the partition function of the gauge theory will be some equivariant Hirzebruch Y genus on the Hilbert scheme of n points on C2, which is the moduli space of these U1 gauge fields, of some, well, vector bundle. That's the field content in the theory. You will have G copies of the, I think, the cotangent bundle of the Hilbert scheme, and there is some shifting factor of a line bundle here. Anyway, you have an equivariant line bundle on the Hilbert scheme of n points on C2. You can, in fact, you can formally define it, but I think this is better than that. You can actually define an equivariant Hirzebruch Y genus to that. So what you have to, I mean, here I am just giving the details of this formula, some tautological bundle. And what's important, of course, is that the torus acts on C2, and this will give us an action on the Hilbert scheme of K points on C2 with isolated, that's the issue, is that you will have isolated fixed points. So this formula, in fact, becomes a very simple combinatorial formula when you localize it to the fixed points of the action. And so this way, and in fact you can take that as a definition, I might take that as a definition, take this localized formula, just localize this as it was as projective already to the fixed points, and that formula, I will show you in a moment, is a combinatorial formula, and that's, you can take the definition of the partition function of this gauge theory on C2 U1 gauge group, but this field content. And then this will tell us this first column of this last big diagram. So namely, this way, you can take this as a definition of the gauge theory partition function. What we are doing here, we are taking all partitions of n, which are labeling the isolated fixed points of the C star, the torus section on the Hilbert scheme of K points, or n points, if that's the same n. And then for each of them, what you do is that you localize this equivariant index here. So here is all kinds of things. The equivariant normal class of the normal bundle of the fixed point is here in the denominator. Here you see this some invariance, the Hirzebruch Y genus locally on this, and tot class. All that is put together. When you calculate it at that infinitesimal point, it will look like this. So the left-hand side, in fact, is nothing but this gauge theory partition function. It's combinatorially well understood. Of course, what we see here is that it's the same thing as our left-hand side, but this now means completely different. In our story, this had to do with the irreducible representations of G on FQ. Here, it has to do with fixed points of this torus section on the Hilbert scheme of n points on C2. So this is, you can take as a definition. Now here you have the geometric engineering conjecture, which is a long succession of conjectures made by physicists, starting probably with Nekrasov and others. And so this culminates in this refined conjecture. Again, these invariants are not defined, but still. Now, if you can take this refined version of the Gopoka-Marvafa conjecture, which may be the central conjecture in the Diaconescu work, the refined Pandari-Pandey-Thomas invariants ought to agree with these BPS, refined BPS state counts, which as they were arguing, Diaconescu was arguing, should be possible to see from the graded pieces of the perverse filtration of the moduli space of Higgs bundles. So now if you look at that formula and do some changes of variables, you will find exactly the same formula. The X was there already, the K was there already, and then all this extra stuff matches up with that formula, and then you had the refined BPS state. Somehow they will just be remembering the graded pieces of the perverse filtration of the moduli space of Higgs bundles. The formula you are getting is going to be exactly the same as our formula for the mixed Hodge polynomial of the character variety, and the two of course agrees. Well, they definitely agree if P equals W, but our point of view in this talk that in fact it gives a very good support for the conjecture P equals W, because what you can do now, and that's the conclusion for the physics part, and then I continue with one more mathematical observation, is that if you put together our conjecture with Fernando, and then what the physicists are thinking, this one is not a conjecture, but this is the geometric engineering is a really non-trivial, very surprising conjecture relating geometry of a Calabi-Yau to some gauge theory partition function. And then you have this Gopoka-Marvafa conjecture bringing in another duality theory, type 2A and M theory. Then if you put these together, all these together, you believe all these conjectures, then, well, it doesn't really imply P equals W, but what it implies is that the graded pieces of the perverse filtration have the same dimension than the graded pieces of the weight filtration. So that's a very strong support. Well, you have to accept at least 3 conjectures. Okay, one was done by mathematicians, so you can have a better feeling about that, but okay. Anyway, so this is, for me at least, the best support so far, the best evidence for higher n, why P must equal W, because the physics says that they must have the same dimensions as the weight filtration. Okay, so let me show you a practical application of this. In the case when genus equals 1, you remember that I said that we were studying this combinatorially and we couldn't prove it. And we still today, I don't think there is a combinatorial proof of this formula. So this is some refined genus equals 1 formula. But what happens is that you can translate everything by geometric engineering by a statement in the gauge theory on C2. And then in that case, now genus equals 1, so only one matter field. And then when you do this geometric engineering business, the same formula can be reformulated in a completely different geometric meaning. If you remember this, we had to do with character varieties for genus equals 1. Now it will have to do with the Hirzebruch Y genus of equivariant Hirzebruch Y genus of the Hilbert scheme of endpoints on C2. And this should equal with some stringy version of the orbifold, the symmetric product of C2. So this is in the this formula here is in the framework of Kontsevich, who thought that you can see the stringy cohomology of orbifold by the ordinary cohomology of a Crepant resolution. This is that sort of formula, but now it's only about the Hirzebruch Y genus. This is now equivariant, so it's a little bit formal. You might think of this being again defined by localizing to the fixed points. And you have a definition on the right-hand side. When you calculate the two sides, you will get these two sides here, formally, combinatorially. So this conjecture, combinatorially, is the same as this one. But as I say, combinatorially is very hard to prove. So, but there was a work of Walder who studied this problem, and this was a really non-trivial geometrical proof, which proved in particular that these two Hirzebruch Y genera agree. And so he proved geometrically, in fact, a more general statement than this. He studied some equivariant elliptic genera. But at any rate, we have a very non-trivial geometrical proof of our combinatorial formula, but in a completely different world. After geometric engineering, it's about Hilbert schemes. So let me finish with the last slide of a mathematical outlook of first summarizing what we have seen is that the work of Chuang, Diaconescu, and Penn explains that the refined BPS conjecture is somehow in a way equivalent with our conjecture with Fernando on the character variety side, and the two can be identified exactly if P equals W in our conjecture with De Cataldo and Migliorini. So that's somehow the summary of today's talk. Let me give you several other points. So one is a very promising direction which actually preceded this work. So before Chuang, Diaconescu, and Penn studied the BPS state story, they had studied just these invariants, which again are not defined, but assuming they are defined of this local Calabi-Yau threefold, you can study the change of stability conditions. You can conjecture what sort of wall-crossing formula these refined invariants should satisfy. And then what they found is that somehow these should involve the Poincare polynomial of the moduli space of Higgs bundles in them. So that's an earlier work. It's somehow a different reincarnation of the cohomology of the moduli space of Higgs bundles. But what it gave was a conjectural recursive formula for the Poincare polynomials of the moduli space of Higgs bundles. It's conjectured in many layers. It uses, of course, the geometric engineering conjecture here. Things are not defined, so it's in a very many conjectural layer. But still, this was perhaps the first time when there was a recursion relations which these Poincare polynomials of Higgs bundles should have satisfied. And this one, in fact, was studied by my postdoc Mozgovoi in Oxford, and he had proved that provided our conjecture with Fernando or a refined version by him is true, at least in the level that these are polynomials. These or conjecture things are a priori rational functions in Q and T. If they are polynomials, then he proves that the corresponding Poincare polynomials solve this recursion relation. So that shows that if someone can somehow do this local Calabi-Yau 3 case study wall crossing in this refined Pandari-Pandey-Thomas theory, that at the end might lead to finally a solution of this long-standing problem of finding the Poincare polynomials of the moduli space of Higgs bundles. So that's one aspect which is outstanding and still very exciting possibility in the future. And the other one is just to put conceptually together what we have seen is this very, it proposes this geometric engineering as deep and mathematically very surprising connection between two unrelated looking objects. Namely, we had studied these equivariant indices of bundles. We were working the equivariant K-theory of the Hilbert scheme of endpoints on C2 and the perverse filtration of the cohomology of Higgs moduli spaces. So very surprisingly, there seems to be some underlying deep connection between the two. And what I can say is that what you can then notice is that if you do equivariant K-theory on the Hilbert scheme of endpoints on C2, you can come up with the work of Hyman, who used McDonald polynomials. He understood McDonald polynomials in the K-theory here. And to that I can say that in a recent work with Letellier and Villegas, we also understand these mixed Hodge polynomials of the character varieties, but if P equals W, then the perverse Hodge polynomials of the Higgs moduli space is using McDonald polynomials. So what might happen is that this geometric engineering might explain the appearance of McDonald polynomials in both. And in fact, there is an even higher layer of possible correspondence because there is a symmetry. The double affine Hecke algebra acts in some way on, say, the equivariant K-theory of the Hilbert scheme of endpoints on C2 in the work of Gordon and Stafford. And it is also expected to act on the cohomology of the moduli space of Higgs bundles. And it might be that some of this double affine Hecke algebra might be the organizing principle via which one can relate these two seemingly unrelated objects. Okay, thank you very much.
We can have a quick question. Okay, then, so we'll thank Tamas again.